Let's read the question. We have a balloon accelerating upwards at 4.9 meters per second squared. After 2 seconds, a ball is dropped. We need to find the maximum height the ball reaches. First, let's visualize the balloon's journey. It starts from the ground and accelerates upwards for exactly 2 seconds. Let's calculate the balloon's velocity and height at this exact moment of release. Using basic kinematics, we find it has a velocity of 9.8 meters per second and is at a height of 9.8 meters. Now here is the classic NEET trap. When the ball is released, it doesn't just fall. It inherits the balloon's upward velocity of 9.8 meters per second. So the ball travels upwards a little bit further before gravity finally pulls it back down. Let's calculate this extra height using v squared over 2g. The extra upward distance is 4.9 meters. To find the total maximum height from the ground, we simply add the balloon's height and this extra height, giving us 14.7 meters. Want a 5-second shortcut? Whenever balloon acceleration is exactly g by 2, the total max height simplifies directly to 38gt squared. Plug in t equals 2 and you get 14.7 meters instantly. Let's read the second question. A body falls from rest, hitting a velocity v after falling a height h. We need to find how much further it must fall to double its velocity. Let's visualize the drop. The ball starts from rest, so initial velocity u is 0. It falls a distance h, and at this exact point, its downward velocity is v. Let's bring in the core kinematic equation that links velocity and distance. V squared equals u squared plus 2gs. Since the ball drops from rest, u is 0. This gives us a direct proportionality. V square is directly proportional to the total height fallen. Now, we want the final velocity to double, becoming 2v. What does this do to our height? If we substitute 2v into our proportionality, we get 4v squared. This means the total height must scale by a factor of 4. The total distance from the top is 4h. Here is a massive NEET trap. The question specifically asks for the distance it falls further. Since it already fell h, the further distance is mathematically 3h. But look at the options. 3h isn't there. In poorly phrased exams, if the exact difference isn't an option, they are asking for the new total distance, which is 4h. Always check your options. Let's look at question 3. A body's velocity reduces by 3/4 of its initial value in time t0. We need to find the total time until it completely stops. Instead of jumping straight into equations, let's draw a velocity time graph. The body starts at an initial velocity u and uniformly decelerates to 0. This gives us a straight line sloping downwards. The question states that in time t0, the velocity reduces by 3/4. This means it drops from u down to 1/4 of u. Let's mark this drop on our graph. Now let's set up the standard kinematic equation. V equals u minus at. Plugging in our values, the final velocity is u over 4, which equals u minus a times t0. Solving for acceleration gives us 3u over 4t0. To find the total time to stop, we set the final velocity to 0. 0 equals u minus acceleration times total time. Substituting our acceleration, we find the total time is 4/3 of t0. Want to solve this in 5 seconds without algebra? Look at the graph. Losing 75% of the velocity takes time t0. Since it's a straight line, losing 100% of the velocity to stop completely will just take 100 over 75 times t0, which simplifies instantly to 4/3 t0. Let's read question 4. A particle starts from rest, accelerates for 10 seconds, maintains a constant speed for 30 seconds, and then decelerates until it stops. We need to find the total distance traveled. This is a classic 3-stage motion problem. The absolute best way to visualize this is by drawing a velocity time graph. Stage 1, the particle accelerates from rest for 10 seconds. Stage 2, it cruises at a constant maximum velocity for 30 seconds. Stage 3, it hits the brakes and decelerates to 0. Let's calculate the maximum velocity reached at the end of stage 1. Using v equals u plus at, the velocity is 2 times 10, which equals 20 meters per second. Now, how long does it take to stop in stage 3? It decelerates from 20 down to 0 at 4 meters per second square. Time is velocity over acceleration, which is 20 divided by 4, giving 5 seconds. The total distance is simply the area under this velocity time graph. Let's calculate the area of the 3 sections. The first triangle is 100 meters. The middle rectangle is 600 meters. The final triangle is 50 meters. Adding them up gives a total distance of 750 meters.
Want a 10-second shortcut? Treat the entire shape as a single trapezium. The total area is 1/2 the sum of the parallel sides times the height. 1/2 of 45 plus 30 multiplied by 20 instantly gives 750 meters.
Let's tackle the final question. A train accelerates from rest to a maximum speed of 40 meters per second in 20 seconds. It cruises for another 20 seconds, then brakes to a stop over 40 seconds. We need the average velocity. Just like the last problem, a velocity time graph is our best friend. The train starts at 0, ramps up to 40, stays flat, and then comes back down to 0. Let's label the time intervals on the x-axis. The acceleration phase takes 20 seconds. The constant speed phase takes another 20, bringing the clock to 40 seconds. Finally, it brakes for 40 seconds, meaning the total time is 80 seconds. Average velocity is total displacement divided by total time. On a velocity time graph, displacement is simply the area under the curve. Let's calculate the areas of the two side triangles and the central rectangle. The first triangle's area is 400, the rectangle is 800. The final triangle is also 800. Adding these gives a total displacement of 2000 meters. Dividing 2000 meters by the total time of 80 seconds gives us exactly 25 meters per second. That is option C. Want a genius shortcut? You can skip calculating separate areas. Use the trapezium average velocity formula. V average equals max velocity over 2 multiplied by the sum of total and constant times divided by total time. Plugging in our numbers gives 25 meters per second instantly. Let's analyze question 6. An open lift moves up at 10 meters per second, accelerating at 2 meters per second squared. A ball is thrown up at 20 meters per second. We need to find when and where they meet. First, let's visualize the exact physics. The lift is accelerating upwards. The ball is thrown upwards from it, but gravity immediately starts pulling the ball down at 10 meters per second squared. To find when they meet again, we set their total displacements equal to each other. S lift equals S ball. Using the second equation of motion for both, we plug in their initial velocities and accelerations. For the lift, u is 10 and a is positive 2. For the ball, u is 20 and a is negative 10. Solving this algebraic equation, the t squared terms combine to give 6t squared equals 10t. This gives a time of 5/3 of a second. Next, what is their displacement at this instant? We just plug 5/3 into the lift's displacement equation. The math gives us exactly 175 over 9 or 19.4 meters. Finally, what about the exact distance travelled by the ball? The ball takes 2 seconds to reach its maximum height where its velocity becomes 0. Since they meet at 5/3 of a second, the ball hasn't started falling yet. Therefore, its total distance is exactly equal to its displacement, 19.4 meters.
Let's read question 7. A particle starts from rest, accelerates over distance L, moves at constant speed for 2L and decelerates to a stop over 3L. We need the ratio of average speed to maximum speed. Let's draw a velocity time graph. The particle accelerates from 0 to a maximum speed Vm. It stays at Vm, then decelerates back to 0. We know the area under a velocity time graph gives the exact distance travelled. The first triangle area is L, the middle rectangle is 2L, the final triangle is 3L. The total distance is simply 6L. To find average speed, we need the total time. We can express each time interval using the visual areas. The area of the first triangle is 1/2 base times height. So L equals 1/2 times T1 times Vm. This means T1 is 2L over Vm. For the middle rectangle, area is base times height. 2L equals T2 times Vm. So T2 is 2L over Vm. For the last triangle, 3L equals 1/2 over T3 into Vm, giving T3 as 6L over Vm. Adding these 3 time intervals up, the total time is exactly 10L over Vm. Finally, average speed is total distance, 6L divided by total time, 10L over Vm. The L's cancel out, leaving us with 6/10 or 3/5 of Vm. The ratio is 3/5, which is option C.
Let's look at question 8. Two balls are thrown upwards with different speeds. We need to find the correct graph for their relative separation delta y over time. First, let's visualize the physical motion. The blue ball is thrown faster and the red ball is slower. As they rise and fall, we will actively plot their separation distance on a graph in real time. Notice what happens while both balls are in the air. They both experience the exact same downward pull of gravity. This means their relative acceleration is 0. Because the relative acceleration is 0, their relative velocity is constant. Therefore, their separation distance increases steadily, forming a perfectly straight upward line on our graph.
But watch what happens right here when the slower red ball hits the ground and stops. The blue ball is still in the air. Now the red ball has zero acceleration, but the blue ball is still accelerating downwards. The relative acceleration is no longer zero, it is g. This causes the separation distance to follow a parabolic curve as the blue ball falls back down. This perfectly matches option D. Want a 3-second cheat code? Just remember this rule. Same medium means zero relative acceleration, giving a straight line. Once one hits the ground, relative acceleration becomes g, giving a parabola. Option D is the instant winner.
Let's break down question 9. We need the correct velocity time graph for a ball thrown upwards, but this time we must include constant air friction. First, let's visualize the forces during the upward journey. The ball moves up, so gravity pulls down. But remember, air friction always opposes motion, so it also pushes down. This means the total downward acceleration is g plus the friction acceleration a. On a velocity time graph, constant acceleration means a straight line, and this one will be very steep. Now let's look at the downward journey. The ball is falling, so gravity still pulls down, but air friction switches direction and pushes up, fighting gravity. The total downward acceleration is now only g minus a. It is still a straight line, but the magnitude is smaller, meaning the slope will be less steep or flatter. Let's check our options. Because the acceleration is constant in both phases, the graphs must be straight lines. This instantly eliminates the curved graphs A and C. Finally, because g plus a is greater than g minus a, the upward journey must have a steeper slope than the downward journey. Option D perfectly shows a steep line crossing 0, followed by a flatter line for the fall. Option D is correct.
Let's look at question 10. The acceleration versus time graph of a particle moving along a straight line is shown right here. We need to draw the respective velocity time graph assuming initial velocity is 0. To solve this, let's set up an empty velocity time graph exactly below our given acceleration graph so that time axes align perfectly. Remember, the area under an acceleration graph gives the change in velocity. Let's look at phase 1, from 0 to 2 seconds. The acceleration is a constant positive 2. Because it's constant, the velocity will increase linearly. 2 times 2 gives a final velocity of 4 meters per second. Let's draw that straight upward line. Now for phase 2, from 2 to 4 seconds. The acceleration drops to exactly 0. Zero acceleration means the velocity does not change. It remains completely constant at 4 meters per second. We draw a flat horizontal line. Finally, phase 3, from 4 to 6 seconds. The acceleration is negative 4. This is a heavy deceleration. The velocity will drop linearly from 4, losing 8 meters per second total, bringing it down to negative 4. Notice exactly where it crosses the x-axis. Since it loses 4 meters per second every second, it hits a velocity of 0 exactly at 5 seconds. Want a visual cheat code? Just memorize the shape mappings. A horizontal block above the axis becomes an uphill line. A block on the 0 line becomes a flat line. And a block below the axis becomes a downhill line. Connect them and you are done.
If you found this visual breakdown helpful, you need to put that knowledge to the test right now. Head over to neetapp.in or download the NEET app today. We have chapter-wise, concept-wise and level-wise MCQs from easy to moderate to hard waiting for you to master. Plus, you can take free full syllabus mock tests, grab premium NCERT-aligned study materials and enroll in our ultimate NEET crash course to supercharge your prep. Don't just watch physics, conquer it. Hit that subscribe button, click the link in the description and I'll see you in the next video.